Hello, everyone. I think we can get started. So this is the seventh session of IoTDI. And please be noted that this Zoom session is being recorded so that those who are in the off zone and off time zone can see the presentations when they woke up. My name is Ray, and now I'm with the Nanyang Technological University in Singapore. And my research is in the networked sensing and also IoT and the sub-physical systems. And this session is about the machine learning for IoT, and we have two papers. Those two papers are all about implementing or using the machine learning in the IoT systems. So for regarding the timing of the presentation, each talk will be 20 minutes. Then after that, we have 5 minutes for Q&A. And during the 2 minutes before the timeout, I will give the presenter a verbal reminder. Okay. Okay, so now let's move on to the first paper presentation. And the title of the paper is ML IoT, an end-to-end machine learning system for the IoT. And the presenter is Suda-san, and he is a third-year PhD student in societal computing at CMU. His research interests are building systems, machine learning, and IoT. And now I hand over the time to Suda-san.
Hello, thank you for the introduction. I'm Sudarshan. I'm a third-year PhD student working with at Carnegie Mellon University, working with Yuvraj Agarwal. Today, I'm going to present a recent work on our vision to build an end-to-end machine learning system for Internet of Things called ML IoT. This work has been done with a close collaboration with my teammates Anurag and Prahal, without whose help I would not have got to this point. So let's get started. Today, with the advent of IoT, there have been several applications in different domains, such as home automation in homes and buildings, healthcare monitoring activities of daily life, and healthcare, preventative maintenance in industry, and tracking of changes in environment in agriculture environments. All of these applications are enabled by the rich sensing capabilities of IoT sensors and devices such as a smart speaker in a smart home, a smartwatch in a healthcare, and a smart meter in an industrial setting, and then a smart drone in an agriculture environment. All of these systems rely on the robust machine learning system, and the goal of the systems is to contextualize your rich sensor data and use machine learning to provide rich inferences. While there have been several advances in the sensor and each of these domains, today we're going to talk about the key challenges in IoT and that needs to be addressed by the machine learning systems. Machine learning systems in general needs to adapt to different IoT requirements. Different applications in IoT have different requirements based on machine learning requirements, such as like accuracy, latency, or training time. And they also have different requirements for where they want to run their task on, either run locally or in a high compute environment. For example, an application in a home would want to have a low latency and would want to also run in a local device. But however, in a healthcare industry, they would want to have their machine learning task to have high accuracy and no bounds on how much resources they have. There are different resource. There are a variety of different resource environments available for different applications. This includes from having a Raspberry Pi to a local desktop computer to a cloud computer or a cloud machine. There is an inherent heterogeneity in these device capabilities in terms of like CPU complexity or the number of cores, the memory, bandwidth, and if it is a hardware accelerator or not. All of these affect the performance of the machine learning algorithms that is used to run the machine learning task. Machine learning systems are also affected by the dynamic nature of the IoT environment. This includes the changes in the ambient environment, which are both transitive or permanent. There are different diverse sensor sources from different modalities, such as camera, audio, and multimodal sensors. All of the machine learning system needs to adapt the machine learning algorithms to each of these different sensor sources so as to provide better accuracy for the application task. Overall, there is a lack of end-to-end machine learning platform that is specific to IoT, and which basically takes in the training, evaluates model, and optimizes optimizes the models and the machine learning task for that particular IoT application. What do current machine learning systems do? We conducted an extensive survey on several machine learning systems that consist of the basic features that are required for a machine learning system to address the challenges of IoT environment. These include providing expressive policy to understand different application requirements, adapt to different resource environments and IoT environments, have an adaptive model selection policy to model selection to adapt to different applications. Overall, we also look at if the system provides an end-to-end platform. However, current machine learning ecosystems support either a certain set of patterns, such as training, and are focused on our individual silos, are basically individual silos of such patterns, which is either training, serving, or hybrid. Let's look at one of the training systems, which is Project Adam, and Helix, which uses declarative programming techniques and distributed training methods to optimize the machine learning workflow for different resources. However, they did not take into account of other requirements. Similarly, the current serving systems are optimized for latency serving latency of black box models, and they did not. And some of these include Clipper, which is a general purpose serving system, and other systems such as Ubiquitix, which is a purpose-specific system which is used for activity recognition models using audio data. Again, all of these systems provide only a subset of features, and not all of them. And the ones which are very close to what MLRT does are also either general purpose or purpose specific. For example, MITES as a system which basically is focused on developing and focused towards serving multimodal sensors. PFX, on the other hand, is over a general purpose serving system. Overall, MLRT aims to achieve all of these features in order to provide an end-to-end solution for an IoT environment. MLRT obtains. How does MLRT do this? MLRT obtains the machine learning tasks for each application, and then it sends it to the two major components of MLRT, which is the device selection layer and the training serving layer. The device selection layer is responsible for obtaining the application policy requirements from a machine learning task and adaptive selection of resources to spawn different training serving instances for the available resource environments. The training serving layer is responsible for adaptive model selection during runtime, optimizing the training and serving for machine learning tasks, and continuously adapting the models to different IoT environments. Now let's look at these features in detail. Different applications have different sources of input, as we discussed, such as camera, audio, and multimodal sensors. All of these information is being sent through the application, and the application provides a different set of requirements. such as accuracy, latency, and training time, what type of devices, and if it needs to run on edge or cloud. MLIT provides a set of expressive policy, which is defined as static and dynamic policy. The static policies take into account of information such as how much resources the particular application requires, or the locality of that particular device or particular task. The dynamic policies, on the other hand, uses information, uses metrics that change, that continuously change, such as CPU load and model latency. So you could think of an application providing a threshold on providing a low latency task, or have a best effort policy. When a system provides a best effort, the MLIT chooses the resource environment with the most available resources that encompasses all their policy requirements. MLIT then runs the training and serving tasks on each of these different devices based on the policies. To do this, MLIT uses an adaptive device selection method to select the available resources across runtime and application requirements. So for example, an application, an activity recognition that requires a low latency and training time and a requirement to run on the edge would basically be sent to the MLIT. MLIT then understands the available resources in each of this device and then deploys a particular training and serving task. MLIT also adapts to the runtime, uses the policy to adapt to the runtime environment. Adaptation, it also adapts the model selection for training and serving based on available resources, and also adapts the machine learning tasks to the machine learning task based on the application requirements. So how does this adaptive selection of model work? To understand this, the MLIT computes different performance metrics such as training time, CPU, memory for each model on the available devices and for different application sources. Here in this graph, we plot the training time, CPU, and memory for different devices such as Raspberry Pi, a 2-core machine, and an 8-core machine. We also select the diverse input data such as image, multimodal, and audio data. And we also pick the popular models such as KNN and SVM that are popular in each of these application domains. We see that on an average, RPi takes more training time and computes resources in general. But we also see that between different application resources, there is a variation. For example, applications in audio take more resources when compared to image or the multimodal sensor data. We also observe that some models, such as this is also similar in other devices. Audio data takes more resources when compared to the other data sources. We also observe that some models, such as MLP and Ridge, can actually better exploit multiple cores and reduce the training time. MLIT obtains all of these relative performance metrics across different devices and then smartly selects the models and the particular application task to run on that particular device. However, in an IoT scenario, over time, additional training samples are added. So how does MLIT adapt to changes in model performance with increasing training samples? MLIT uses existing model optimization techniques such as dimension reduction and hyperparameter optimization. Dimension reduction helps in reducing the feature space, reducing the model size and the complexity, and hyperparameter optimization optimizes the model based on the input. This figure shows the training time, accuracy, and latency of using DR, the dimension reduction and hyperparameter optimization individually, together, or without. We see that enabling the dimension reduction and HPO reduces the training time and increases the accuracy. However, there is slightly higher increase in the uh, 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 latency. This is similar to what we see in other as we increase sample size, where we see that the training time decreases, accuracy remains almost same. However, the latency is comparatively higher. Uh, Additionally, we also see that uh, when only HPO is enabled, which is hyperparameters optimization is only enabled, we see that the latency decreases and there is higher accuracy or similar accuracy and slightly higher training time. So this allows MLIT to quickly choose between different techniques. So if an application requires a higher accuracy, then lower training time, it basically enables DR and HPO. And when an application requires low latency, it only enables hyperparameter optimization. So with more and more optimization, and we start training more complex models, models in an ensemble, it takes a longer training time. This results in higher latency to start serving the first request. MLIT uses a lazy training technique where the models specified by the bounty are sent to the serving side and complex models are trained in the background with lower resources in a lazy manner. So how does this work? The application uses the time bounds for each of these models. It sends the training worker. The training worker assesses the training time, the runtime training time, and then understands what is the threshold. If the model has exceeded the threshold latency, then it basically sends a lazy training. If it hasn't, it goes to model serving. Once a lazy training completes the training, it sends the model serving, basically increasing accuracy over time as more and more complex models being trained. Another important feature that we found while testing MLIT in real world environments was that we realized that the model serving could be optimized better. Most continuous serving IoT scenarios are dominated by periods when there is no event happening. For example, an activity detection application, there may be almost 8 hours of a day when an occupant is almost asleep, and the output is basically ambient background. Similarly, there are other applications where only one particular activity is happening continuously. Where existing machine learning systems use multi-class models instead of this leads to higher latency and lower accuracy especially when there's background noise. To overcome this, MLIT proposes a two-stage system where the first stage is basically a binary classifier, which basically detects background or not, and it is able to the majority of the time it basically detects if it is background with a lower latency when compared to when there's an ensemble of models. So overall, how does all of these come together to play? This is overall system architecture of MLIT. The device selection layer has the key roles, as we discussed, to spawn training serving instances for different machine learning tasks. It also takes application requirements and also runs a particular task given the resource environments on each of these machines. Every machine, such as a Raspberry Pi or a cloud compute, will have a manager which continuously monitors the changes in each of these devices. Every task is a coupled training and serving instance, which allows us to provide a continuous feedback loop in case there is feedback. So how does this work in a real world scenario? There is various feedback sources obtained from different people. They request from users or smartphones or from buildings, which request for a machine learning task to the application. The application requests a particular device, and then it spawns the training and serving instance on a particular machine. Then the application uses the data and sends it to the assigned training and serving instance. The assigned training and serving instance uses the model specified by the feedback sources and sends back the prediction. The feedback sources then provide feedback based on the prediction if it's correct or not. And then this information is basically used in the serving side to adapt the model and also retrain the model itself. The key here is the close coupled training and serving, and policy-driven continuous adoption for training and serving. How does the training and serving worker work? The manager spawns training and serving workers. The training data is obtained from the different sources. It also obtains the untrained models from different applications. It uses DR and HPO to optimize the model. It creates the trained models, and the models which are taking greater than threshold, it runs on the lazy training side. All of the trained models are sent to the serving worker. The serving worker has three major components: two-stage, ensemble, and model selection. The model selection uses the input from the application requirements and selects a model based on what the application requires.
2 minutes left.
The prediction input is then taken by this two-stage system. If it is a background, it makes a background prediction. If it is not a background, it sends an ensemble prediction. And then it sends the ensemble prediction value. Finally, the aggregated feedback is obtained from the feedback sources. It is used to update the model. Model optimization basically chooses the best model, and feedback based continuous model adaptation allows the system to adapt to different IoT scenarios. So how to evaluate MLIoT in real world, we ask the basic questions. How well does MLIoT adapt to different IoT settings? How well does it adapt to different resource environments? And how well does it adapt to different policy requirements? How well does it scale? And how well does it compare to existing systems? We basically choose several test beds with different device configuration, resources, and network requirements with both local and cloud. We also choose the benchmark applications such as MNIST and MITES and MITES, which is basically multi-model classification data set, and microphone, which we collected by ourselves. To see how well the system adapts to the available compute, we co-located machine learning tasks on a single machine. As it increases from we co-locate machine learning tasks on a single machine. We can see from 1 to 8 on a particular machine, and then calculate the latency. We see how the baseline linearly increases. And then for each of these tasks, we have a latency of a policy bound latency of 400 milliseconds. We see that over as more and more instances are being added, the number of models being served in each of these instances are reduced. The average accuracy across the system is reduced. So for example, at 4, when a new training and serving instance is added, it realizes that the system realizes that MLIoT realizes that the overall latency becomes greater than 400 milliseconds. So it drops and models across different instances. And we see that it also tries to maintain the accuracy across the same value. So basically, as co-located machine learning tasks increase, MLIoT drops models and to maintain accuracy of machine learning tasks and meet the latency bounds.
All right. So can you wrap up soon?
Yeah. So here we show the real-world execution of how the system handles 2 machine learning tasks for different IoT workloads. We have 6 machine learning tasks for different diverse policy requirements, compute resources, and metrics. The different colored boxes show the labels for timeline of execution. On the left, we see that different resource environments that is used to spawn these tasks. The RPI and NUC are edge devices and have low latency. We show that as the system scales, for example, T1 picks the local device, and then as P2 comes in, it picks the low latency machine, which is RPI4, and then the P3, which is the best effort, picks the best device possible. And then when T4 comes in, it basically picks the best device with the average latency higher. So and so on, it basically continues. We also see the interesting aspects where certain application tasks are, for example, T9. We also see certain aspects where MLIoT basically adapts to different resources and then moves the training and serving tasks between different compute resources. We then compare our system with the state of the art ubiquitous system, the state of the art application-specific machine system, which is done activity recognition based on audio data. And we also classify with the general purpose system. We see that ML-IoT improves accuracy by 71%, while keeping the latency around the same value. When ML-IoT run with the policy of low latency, it has a value of 0.06, almost lesser than the ubiquitous text. When we run the general purpose system, the overall accuracy, when we run the general purpose system, such as TensorFlow Extended, our system improves accuracy by 32% while incredibly reducing the latency when we run ML-IoT with the low latency policy. We also test with the multimodal sensor system, which is specific system, which is MITES. And we see that our system improves accuracy by 75% while slightly higher latency. When we run it with low latency policy, it has lower latency. Overall, ML-IoT improves accuracy from 50 to 75% while reducing or maintaining the latency. ML-IoT provides policy-driven selection of hardware platforms, models, and various optimization, integrates different distributed components, and overall, it basically provides an end-to-end machine learning system that supports the entire life cycle of IT application. Thank you. I'm sorry, I went a bit too well.
Right. Okay, so now it's Q&A. So if you have a question, you are encouraged to unmute yourself and talk to our speaker directly. Or you can also, just type your question.
Hello, can you hear me?
Yeah, we can hear you.
I am Tamur. Hi, Sudarshan. It was a good presentation. So I have a couple of queries about this work you would like to may answer. So my first query is that how does this system, handles time series data? If data is, time series, would it handle it differently, or it doesn't matter for the system either data is time series or not?
So all of the data, that's a good question. All of the data that we are looking at right now from audio or like multimodal sensors, all of these are time series data. And we are benchmarking a system based on these time series data. For example, the MITE system that you're saying, the data is collected at 1/10 of a second. So it's a very high fidelity data set that we're using to benchmark a system already.
Okay, thank you. And the other question is like you guys have evaluated the system using the freshly collected sensor data, or you use some sort of data set available publicly?
We did both. So when we are testing ML-IoT in real world, we do the runtime testing of how well the accuracy changes or how well the accuracy of the system adapts. So we do get the real world continuous data that's being obtained from the sensor sources.
Okay, and you said you used both of them, like already collected data and the ones you guys already by self collected. So is data which you have used data set is available publicly, or which data that you guys have used for specifically? I am interested in multimodal sensor data.
Yeah, so for the camera and the audio one, we use the public data, which is already available on each of the platforms. For the multimodal sensor data, we collected from our own devices, and that is not available here, but we can share if needed.
Okay, thank you. Makes sense. Thanks. Good luck.
Yeah, thanks.
All right, so any more questions? All right, so there is one question in the chat box. How does ML IoT improve accuracy? Maybe, I guess, yeah, he missed some part of the presentation.
Yeah, hey, there are multiple ways ML-IoT improves the accuracy. One of them is majorly using the corrective feedback from the users, where when there is an incorrect event happening or a noise happening, we use this feedback to adapt a particular model based on the user feedback. The other ways that we're improving accuracy is using different techniques, such as we discussed, was using different techniques such as dimensional reduction and programming optimization, and how we are basically updating their accuracies. And we are also using two-stage serving, where we improve the accuracies for activities or classes which are continuously happening over time. I hope that answers the question.
Okay, thank you. Right, so there is another question. Is this framework open source? In fact, I also have the same question.
So currently, we don't have this system open source, but we are deploying the system across an entire building with different sensor sources. And there's a bunch of processing that's happening to evaluate the system by the campus official before we can make it open source. But eventually, we see it open source. And once it is open source, we will publish it on the website or on GitHub.
Okay, so I have one last question, which is, can you comment on what are the major technical challenges that you address in this work?
So there are several challenges. One, basically, we don't have, we are basically addressing different challenges in IoT. We don't have an end-to-end system that adapts or adheres to the application requirements. And it actually started off as a work that we wanted to, after we testing out all the existing systems, and for us to use all of these different systems, we had to make it it becomes really complicated to make a product where we can start using these data. The other major technical challenge is to understand how the IoT data changes, what happens with the noise, and how the models react to these noises in the environment. So MLIT basically understands all of these three facets together, and then provides probably a higher accuracy model with adhering to the requirements from the users.
Okay, thank you. And thanks for the nice talk. And for the sake of time, we will need to move on to the next paper. All right.
Thank you.
So can the second speaker set up the slides?
Yeah, hello.
Yeah, all right. Okay, so yeah, so our next speaker is Yilin Liu. He is a PhD student at Penn State University, and his research interests include the cyber-physical systems, IoT, and the human behavior sensing, and also the mobile and the wearable computing and the machine learning applications. Now, please go ahead.
Okay, thanks for the introduction. And I have the pre-record video for my presentation, so I just play it. Hello, everyone. My name is Yilin, and these are my co-authors, Shijia and Mahans. We're from the Penn State University. Today, we will introduce our work on zero-shot domain adaptation for finger motion analytics with inertial sensors. So finger motion tracking enables exciting IoT applications, such as the following. In sports analytics, analysis of finger motion of aspiring players can be compared to experts to provide automatic coaching supports. In healthcare, the finger motion stability patterns are known to be biomarkers for predicting motor neuron diseases. And sign language, as well as augmented reality or virtual reality, are some of the other applications that benefit from finger gesture tracking. So there's a surge of recent research motivated by the above applications. But our question is, why we choose wearable sensors? So many computer vision works can track 3D finger pose from molecular videos. However, vision-based techniques are affected by the issues such as occlusions and the need for good lighting conditions to track finger motions. In contrast to vision, the main advantage of the wearable IoT devices lies in enabling ubiquitous tracking without external infrastructure while being robust to lighting condition and occlusions. So however, also unlike vision, we lack large-scale training data to develop robust machine learning model for wearable devices. So therefore, in order to overcome this gap, we want to present our system called ZeroNet. The high-level idea of our system is very simple. So we want to collect some video data from public website and then somehow convert it to wearable sensor training data for training our finger tracking models. So then we will briefly introduce the overall process of our system. So first, appropriate sources of public available videos like YouTube, etc., are first identified as candidates of our training data. And then the finger locations are extracted from this video using the computer vision techniques. Then the appropriate motion metrics that can be captured from IMU and then derived from these finger locations. So let me give you an example. For accelerations, we perform finite double differential as indicated by the equation here, which extracts the accelerometer data AT from the location PT extracted from the video. So similarly, we can also compute finger orientation by knowing this MCP and PIP joint location. So let's come back to the main process of our system. The training data extracted from the video is further enlarged using data augmentation techniques to create a large and high quality training data set. Then such synthetic data set are used for training our machine learning model. And finally, the trained model can be deployed directly for inferences on wearables devices with zero training overhead. So in this paper, we will use sign language gestures for validation, and we will go into the detail later in our evaluation section. So when we implement the above system, we realize harvesting training data from videos for performing inferences on IMU is challenging because of the following reasons. First, the IMU and camera have differences in sensing modalities, coordinate systems, etc. The second challenge is the speed and orientation of gesture, and body size can differ across users. Similarly, the sensor varying positions and orientation can also vary due to natural errors in sensor placement. which might cause the distribution of training data and testing data not match in the end. So in order to solve that challenges above, we have the following pre-processing to the data from the video and IMU sensor. For challenge number 1, the IMU sensor gives us data in its own local frame. So we need to convert it into global frame using this equation, and then align it with the camera's frame. So regarding the rotation metrics, we estimate it by combining the gyroscope sensor data with the orientation result from the gravity and the magnetometer. Then for challenge number 2, first of all, different users might have different body size. So we do body size normalization to all the training and testing data. So during the training, we normalize all location estimates from camera to the size of the standard human. And in the test, the accelerometer measurement from the human is similarly scaled depending on how the shoulder's length compared with the standard length. Second, we also realize that different user speed and orientation of the gesturing may vary. So we did data augmentation to generate synthetic training data from different users, which can make our system more robust. So let me show you some example of how we did the data augmentation. So first, we did gesture speed augmentation. The speed of the hand motion is one of the metrics that can vary across users. Various parts of the gesture might be performed at a faster or slower pace by different users. So in particular, we stretch and compress different parts of the training data with different factors to create new training data from existing samples. Second, we also do orientation augmentation. Similarly to variations in gesturing where users perform at different speed, the orientation of the hand can also vary during motion. Such variations can happen because of the minor change in the sensor varying position or orientation across users. So we also add some smooth variations to the augmented data. The third one, we do temporal clipping. Different users might start the gesture from slightly different positions, as well as end the gesture early or continue the actual motion beyond the gesture. To simulate this, we augment training data by introducing versions of training data with minor extrapolations or trimming of samples at the beginning and end of the gesture. So after we have the large amount of training data, we also explore 2 methods for exploiting this training data for doing gesture recognition on the IMU data. First, we start with the dynamic time wiping, which is DTW. Briefly, DTW is the pattern match system. It's a pattern match technique that inspects the overall shape of 2 signals to determine their similarity, like what is shown here on the slide. So DTW is known to do a good job of matching such series with similar overall shape, and also measures a difference between the 2 series, determines the similarity score among them. So besides DTW, towards increasing the robustness of the recognition, we also take a data-driven machine learning model. The architecture of the model is shown here on the slides. The input data includes the IMU acceleration and finger orientation. And after we go through the neural network, we get the 50 class softmax output which give us the gesture recognition result. So then we will briefly show the evaluation part of our system, ZeroNet. So in the training side, we initially collect some ASL tutorial video, which is publicly available in the following links. Then apply recent computer vision algorithms to get the 3D finger joint locations of each frame, which will give us finger acceleration and orientation to form our training data. So in the test side, we conduct the user study with 10 users, including 7 males and 3 females. The users are aged between 21 and 32. So each user performs 50 ASL words, and these words are in the dictionary of the most frequently used ASL words. And here is our evaluation platform. The user came and wears a button-like sensor as a ring on their index finger. The sensor streams data wirelessly to a smartphone, which runs as a machine learning model for the gesture recognition. The ring generates 9 axes of IMU data, 3 axes each for accelerometer, magnetometer, and gyroscope, which forms the input data of our system. Then let's see some key evaluation results of our system. This figure shows the overall accuracy as a function of users. So evidently, we can see the accuracy is stable across users, body size, motion patterns, etc., which is because of the inbuilt robustness to such natural variations through the data augmentation techniques incorporating the design of our system. Well, the top 1 accuracy is about 82%. The top 3 accuracy is around 95%, which indicates promise for the future improvements. So also this graph shows the performance comparison across techniques. Here DA means data augmentation. So basic DTW method already achieves a reasonable accuracy of about 60%. On the other hand, the accuracy of the basic CNN model is slightly lower than DTW because of the inability to generalize diversity in user motion patterns. However, the data augmentation technique in our final system, ZeroNet, can make the CNN model robust to speed of gesturing, sensor position, orientation variation, and noise, etc. Thus boosting the accuracy to about 82% in the end. So this graph shows the comparison between training with synthetic data and real data, and also effect of the size of synthetic data. The x-axis label denotes the size of the synthetic data in multiples of the size of the real data. So you can see the higher size of the synthetic data creates more robustness in the training examples that the machine learning model sees during the training. The overall accuracy improves with data size and ultimately saturating when size of the synthetic data is about 40 times of the real data. So overall, our system ZeroNet shows the feasibility of harvesting training data from videos for performing inferences on IMU for finger gesture tracking. We also design a systematic pipeline that fuses data processing and data augmentation technique for better generalizable for machine learning models. And also we conduct evaluation with diverse users that shows a high accuracy over 50 gestures. So I think that's all. And thank you very much for your listening. I will be very happy to answer any questions.
Okay, thank you for the presentation. And now it's a Q&A. We have one question in the chat box, which is from the Ziqi Wang. The question is, how did you manage to extract the 3D joint locations from the 2D images?
Yes, we are using some kind of computer vision techniques, which is called the monocular total capture. I think we cite that paper in our paper in the part we talk about the extracting locations 3D from the 2D images. Yeah, that's a good question. Thanks for that.
Okay. All right. So any other questions, you can unmute and speak to our presenter. Okay, so I have one quick question for you. I think the key advantage of this approach is you can leverage a lot of video data to mitigate the scarcity of IoT data. And do you have any requirements on the video data? For example, do you require the video has to satisfy certain the light condition, and also how the relative angle of the camera and the human subject in the video?
Yeah, thanks for the question. I think most of the public videos are good to our system. Except for some very bad conditions, like you cannot see the person exactly, or some part is getting occluded by especially the hand motion is occluded by some objects like that. That is not feasible to our system.
All right. And do you foresee that you in the future your system can leverage a large amount of video on YouTube, for example?
Yes, we are currently working on that, and our goal is to make our system more robust to more videos publicly.
Okay. And any more questions from the audience? All right. So if there is no more questions, then we will end this session here. And but if you still have, if you want to discuss with the authors, I think that is still the Slack channel that we can communicate. All right. So this is the end of the session 7, and the next session will be starting in about half an hour. And the topic of the next session is smart communities. All right. Okay. Thank you, everyone.
Hello, everybody. Welcome to the 8th session of IoTDI. My name is Amy Murphy. I am a researcher at a research center in Northern Italy. I am the session chair, and so I am not that important today, but the people who are important are the two speakers in this session. We have two really interesting papers on smart cities and applications for smart cities. The first presentation is going to be given with the video, and the second one is going to be live. I encourage you all to pay close attention to the presentations so that you can be ready with questions afterwards. You can write in the chat to me if you have a question, or we'll probably just open up the microphones afterwards and let anybody ask their questions live. If you'd also prefer, you can write your questions in the chat, but there were not very many people right now, so I think it's better to have a conversation. All right, so the first talk is going to be by Tung-Chung Chang. He is a PhD student at the University of California in Irvine. His research interests include the wireless MAC protocols for IoT devices and network analysis in computer networks and social networks. Right now, he's focusing on the development of meaningful tools for incorporating IoT systems into smart community design and operation, and that is the topic of his presentation today. So, he is here with us today. There you are. Thanks for turning on the video. And now I would ask the host to go ahead and play the video.
I guess I will play the video.
Oh, you'll play the video. Okay.
Yeah.
Sorry.
Okay. Yeah,
Misunderstood
okay.
that. Go ahead.
Okay. Thank you for your kind introduction. Okay. Let me pull out my screen. Okay. Can you see my screen now?
Yep, it's working great. Go ahead.
Okay, so let me play my video right now. Hi everyone, I'm Tung-Chung Zhang. Today I'm going to present smart parcels, which helps instrumenting smart IoT applications for smart communities by considering different layers. First, according to this article in Forbes, future cities bring together infrastructure and the technologies that can improve the efficiency and the flexibility of how cities operate. For example, Barcelona saved 75 million euros by using smart management. Amsterdam monitors different situations through real-time data. Smart trash cans are used for efficient pick-up routes in Boston and Baltimore. The Internet of Things is the key technology in these applications, which usually contains sensing, communication, and computing devices. Hence, we need an urban planning tool to assist us in instrumenting IoT applications. So the existing urban planning tools focus on the design of the buildings and the impacts on surrounding areas. For example, in academia, tools are implemented for energy efficiency, which aims to reduce the energy consumption of the buildings. Also in industry, the product of Sidewalk Lab owned by Alphabet mainly recommends the design or plans based on some metrics like capacity and energy efficiency. What is needed for planning smart communities is the ability to select and deploy technologies to create a comprehensive and cost-effective plan to meet the customized application needs of communities. Here are some example applications. First, communities at the wireline urban interfaces, usually called WI, may require Wi-Fi detection, and it can be implemented through image-based or emission-based detection. Second, air pollution is an important issue that could be required by some communities. Then gunshot detection is also an important application, which could be implemented by triangular localization. Finally, noise is also a big concern of some communities. According to CDC, people could have hearing loss after being exposed to noise for 15 minutes. How to implement each of these applications could be a big project. For example, the Wi-Fi project at UCSD. But in this paper, we focus on how to instrument different applications altogether to some communities. For example, two data sources can be used for Wi-Fi detection. The accuracy could be different. Which one should be used? Some data can be reused for different applications, which can reduce the cost. For example, PM 2.5 for both Wi-Fi detection and air quality monitoring, and the sound for gunshot detection and noise monitoring. To sum up, the challenges to instrument applications together in smart communities are the following. Here is a map of Irvine and 4 communities. Each requires 1 or 2 applications. The first challenge is how to choose different devices for each required application, like sensing, networking, and computing devices. Also, different sensing devices may have different accuracies. The second one is where to instrument the selected devices. Different locations have different results. For example, if we are deploying sensing devices and these are the devices we are selected, deploy them to different locations can have different sensing coverage. Similarly, for networking devices, we will have different communication coverage for different deployments. Finally, we need to select computing devices and deploy them to the communities. Also, we need to ensure the network connections. The last challenge is how to reuse the devices under fixed budgets, which trade-off between the sensing accuracy and the deployment efficiency. Intuitively, using expensive devices usually leads to higher accuracy. For example, using images for wildfire detection. However, we can deploy more lightweight devices, which leads to higher coverage of both sensing and communication. For example, we can use the air quality sensor for both wildfire detection and air quality monitoring. In this work, we want to solve a cross-layer IoT planning problem and provide a comprehensive plan of deploying the aforementioned devices under fixed budgets. We propose a framework called Smart Parcels, which considers several layers from application, information, infrastructure to geophysical. First, let me introduce the profiling stage of these layers. We have a set of communities which is divided into several service sites. Each service site is a location that asks for the applications. For example, we have 3 communities. One of the communities, a plaza, has a service site, a bank that requires gunshot detection. Then the communities jointly provide a set of candidate locations for instrument devices. Also, each application can be implemented by a set of information flows, which are flows of information units. An information unit could be raw data or middleware services. Moreover, each information unit has its own QoS requirement, like bandwidth, minimum computing resources. Different information flows have different accuracy. For example, using images for wildfire detection has higher accuracy. Hence, each required application has a structure like this. Then each information flow can be implemented by a set of infrastructure flows. For example, we can put the broker and the virtual sensor separately or on the same edge server. Infrastructure is a device that has computing resources and the network resources. Also, it has its own transmission range and the sensing range. Then 2 costs are associated with each candidate location. Deployment cost, a one-time cost like the cost of devices or labor, and operational cost, a periodical cost like electricity bills. Hence, a tree structure is derived to represent the cross-layer relation between these profiles. In order to instrument the required applications, Smart Parcels selects an information flow for each required application. Then an infrastructure flow is selected for each selected information flow. However, each device has resource constraints, and the total cost cannot exceed the budget constraints. Finally, each infrastructure has a set of geophysical mapping functions. Each maps it to a candidate location. For example, we have an infrastructure flow. One of the infrastructure is mapped to this candidate location. After mapping all the infrastructures, we can derive the service utility for an application required by service side, like this one. The service utility is the multiplication of service accuracy and the sensing probability. Service accuracy is inherited from the information flow. The sensing probability is the probability that a service side is covered by instrumenting this infrastructure flow. First, if this flow is not connected by the network, the sensing probability is 0. Otherwise, smart parcels compute the sensing probability based on the attenuated truncated model. Also, the total costs are determined after the mapping. Hence, a mapped infrastructure flow, MIF, is derived for each infrastructure flow, which has a service utility and costs. What we've seen is the mapping of one infrastructure flow for one service site. How about multiple infrastructure flows for multiple service sites? Can we reuse some infrastructures? After profiling and the geophysical mapping, smart parcels can derive a set of MIFs of each infrastructure flow. Hence, the question is converted to how to generate and select an MIF for each required application. This is the considered cross-layer IoT planning problem. First, two designs are considered. Clean slate, which designs the communities from scratch, and retrofit, which exploits existing devices in the communities. Then the first problem is geophysical mapping selection that generates a set of MIFs by selecting the geophysical mapping functions for each infrastructure flow of the required applications. Second, planning graph generation builds a planning graph by selecting the generated MIFs such that the total service utility is maximized under the budget constraints. Note that if two identical infrastructures are mapped to the same candidate location, we can reuse the infrastructure. Let's say two identical infrastructure is mapped to this node. We can deploy only one. Smart parcels provide several algorithms for geophysical mapping selection. The first one is enumeration, which searches all possible mappings for each infrastructure flow of all required applications. Then each derived MIF has its own service utility and costs. Selection has policies to prune out less promising mappings at the runtime of enumeration. First, mappings with higher utilities should be selected, like these three mappings for the sensor, because closer mappings have higher utilities than others. Similarly, for network devices, those mappings with higher communication coverage are selected. That is, the mappings covering more candidate locations are selected. The last one is retrofit, which considers the existing devices while executing enumeration or selection. If an existing device is identical to the infrastructure can be mapped to the existing devices with no deployment cost. After deriving the NIFs, we can transform the tree structure of multiple applications to the right boxes. Each required application can be implemented by several MIFs, and each MIF has a service utility for some of the service size and its cost. Note that MIFs indicate where the infrastructure should be instrumented and which information units are running on each infrastructure for each required application. Then the plan graph generation selects the MIFs for required applications to maximize the total service utility under budget constraints. That is, the MIFs with higher total utility, which is the sum of the blue boxes, should be selected. The first planning graph generation algorithm is dynamic programming, which recursively includes one MIF. I will skip some details here. Note that after we include the first MIF, the deployment cost can be deducted if some infrastructures can be reused. The process stops when one of the constraints is violated for all MIFs, or all service sites are covered. And then the plan graph is generated. which indicates how to instrument the infrastructures and the information units for applications. The second algorithm is maximum reusability, which iteratively includes one MIF with the highest reusability. Reusability contains investment efficiency, which aims to choose the MIF that has higher service utility but with low costs. The second parameter is the communication coverage, which aims to use fewer devices to cover more candidate locations. For example, instrumenting network devices to these candidate locations has higher communication coverage. Besides, user can specify the weights of these two parameters. Finally, maximum reusability plus executes dynamic programming first to derive a better result, but with higher complexity. It is stopped by user-specified criteria like execution time. Then maximum reusability is used to generate a plane graph based on the partial result of dynamic programming. To sum up, Smart Parcel provides 6 algorithms. With different combinations, it can output a plane graph which could be optimal or pure heuristic. Some hybrid method is provided for partial optimal results. Also, retrofit design is supported. We conduct experiments on 2 testbeds. The first one is a smart campus testbed at National Tsinghua University in Taiwan. We collect locations of streetlights from OpenStreetMap. 8 of them are smart streetlights, and the other 63 are regular ones. The smart streetlights have some existing devices like cameras, motion sensors, and so on. The application required is auto-dimming for energy saving, which 2 methods with different accuracy could implement. We assume all streetlights are candidate locations and service sites. The second testbed is a smart city in Irvine. 4 communities are considered. Also, we collect the public facilities and assume them as candidate locations. Here are the required application of the communities. We first divide the communities into several grids, and then assume the service sites are the center of each grid. We derive the accuracy by real data or from literature. 2 network options are provided, which are Wi-Fi and LoRa. We test Smart Parcel's algorithm by comparing it to a baseline algorithm, maximum utility, which iteratively includes an MIF with the maximum utility. The performance metrics are overall utility, the number of included MIFs, service rate, which is the fraction of applications provided by the plane graph, and the cost performance index, which is the ratio of the overall utility to the overall cost. First, we test the clean slate design in the smart campus. Enumeration is selected as a geophysical mapping algorithm. Different ways of reusability are used for Smart Parcel's algorithm, MR, which is indicated by E and C. Also, purely considering investment efficiency and communication coverage are denoted as if and COF. As we can see, MR with this setting has the best results since the investment efficiency is important, but communication coverage is still relevant. With higher communication coverage, fewer network devices need to be instrumented. This is why the red line performs better than the light blue one, which considers only investment efficiency. Also, MR performs 2 times better in terms of overall service utility as compared to the baseline algorithm MU. MR also implements more infrastructure flows and provides the highest service rates, which means more applications are implemented. Finally, MR derives a higher service utility per spend as compared to MU. Then we study the pruning effect of selection while selecting MIFs. 2 pruning criteria are used, top M service utility and top N communication coverage. As we can see, selection reduces a huge amount of generated MIFs. But MR can still maintain a certain level of overall service utility as compared to using enumeration, which means selection prunes out less promising MIFs. Using a combination of enumeration and MR derives the highest utility, which is the red line here, but it includes fewer MIFs than selection. Seeing more possible MIFs leads to higher utility, but the search space is much larger, as you can see in figure A. Finally, MR derives similar service rate by using selection and enumeration, which means the pruning does not affect it. Here we test MR plus, which trade-offs the optimality and the execution time. Enumeration is used to generate MIFs. The stopping criterion is that DP, dynamic programming, will stop after it includes k-MIFs. As we can see, the time increases drastically when k increases, and the number of candidate locations increases. On the right-hand side, we can see the trade-off between the execution time and the service utility. That is, larger k has a better overall service utility, but execution time is much longer than others. We also test the retrofit design. The existing devices are used in the smart campus setting. Retrofit is used with enumeration. As you can see, MR still derives better overall service utility. And the utility gain after exploiting the existing devices of MR is almost 8 times of MU. To conclude our work, we proposed smart parcels for urban planners, which has 2 designs, clean slate and retrofit. Also, it provides the ability to trade off efficiency and optimality. Some future directions of these works are rapid analysis of some queuing models that can provide end-to-end performance, explore the dynamicity of the system by using something like SDN, and some theoretical extensions like approximation ratio analysis and the formal method analysis. Thank you for your attention.
Okay, thank you for the presentation. We have at least 5 minutes for questions. If anybody has a question, you can go ahead and open your microphone and ask your question. I don't see any in the chat. So maybe while we wait for the first question, I'm intrigued. I'll ask the first question. So I'm intrigued by the notion that you have this notion of a utility that that you can trade off, that you can raise or lower the utility based on the sensors. Can you talk a little bit more about how that plays into the whole optimization process and the overall flexibility that gives you?
So the service utility is combined by the accuracy of the application we can provide and the coverage of this of the application we implemented. So this is a multiplication of the accuracy and the sensing coverage. And the user can also specify some weights of these 2 different metrics. So if someone wants to specify higher accuracy, they can use a higher weight. So by this service utility, we can choose, we can instrument applications by jointly consider the accuracy and the sensing probability.
In the work, you talked about having multiple phases to refine the solution that you're coming to by going up through the stack and mapping different elements. Can you talk about which layer you saw the most constraints, or where was most of the time spent in the refinement process?
You mean the 4 layers?
Mm-hmm.
Oh yeah,
exactly.
So first, the simple part is we know how to implement each applications. So we know the software we need and some bandwidth criteria we need. But in order to put all these software onto the infrastructure, which is the devices, we need some profiling stage. So for this stage, we find the parameters from specifications or from some rule of thumbs, these kind of things. So if in the future we want to further extend this work, we need to more work with some like engineers or some experts in some domains, so we can get more feedback from these parameters.
I'm going to continue asking questions, but if you have a question, you can just interrupt and turn on your microphone and ask. So my next question is, because I read your paper. In your paper, you make this nice analogy that the kind of planning solution that you're coming up with is at a much grander level than some of the initial kinds of network planning that maybe some of us are used to seeing from maybe 10 or 15 years ago, where we looked at how to place network nodes for a wireless sensor network or in a Zigbee network, or where do you place them in order to ensure that you have connectivity? I understand that you are looking at bandwidth as well, and coverage for the sensing, which are two other important parts of that. Were you able to take any other inspiration from that old work on the mapping and the network planning in order to do that layer of your planning system, or did you start from scratch and do planning based on some other criteria?
So let me rephrase your question to see if I understand the question. So you are saying if we can use some old work like Zigbee's or something like this to incorporate these works to our
No, I'm saying that 10 or 15 years ago, we were looking at Zigbee networks for the first time, and we were saying, we don't know where to place the nodes. We have to make sure that we place them so that they stay connected, so that we manage to collect all of the data, that we don't overload the network and all of these things. And so people came up with these very complicated heuristics to decide where to place. You already have some interesting constraints because you're looking at placement locations in the community that are more restricted. I can't place it anywhere. I have to place it on a light pole. But I was wondering if you had looked at any of that old work and were able to use some of the crazy ideas that people had for how to decide where to place the network nodes, or if yours was maybe an easier problem because you already had a constraint for the placement.
Yeah, so for the old work, I'm not sure how they do this, but I imagine they also have some place or some input, given place they can put these devices. So right now, because we are using the public facilities, is because that is more reasonable in smart cities. So because we cannot put the devices on the road or something like this. So if we want to incorporate those kind of works into our work, we also, I mean, the given locations is kind of similar for these two kinds of work, because for sensor networks, they also cannot put the devices onto the road or something like this. Yeah, but of course we can. I mean, for the candidate location, we can, if the cities or the residents allows us to put the devices onto these locations, we can make these locations as our candidate locations.
But the more locations that you have, the harder the problem is going to be, and the more time that you're going to take, right? So is that necessarily a good thing?
Not quite. Yeah, so it's kind of like a trade-off. This is why we have the MR plus thing. So we have the we can trade off between optimality and the time, right? So if the candidate location is, the number of candidate location is huge, we can use pure heuristic to get our result fast.
I have one last question. Unless anybody else jumps in, I'm going to ask my question.
So Amy, if I can sort of interject, I think that was a very interesting question. And in some ways, the problem is easier because, you can't deploy anywhere you wish, right? Mm-hmm. But in some ways, you're also looking at a very different class of communication and sensing technologies than Zigbee, which gives you, everything is not uniform, right? So that the non-uniformity in either the sensing coverage or the communication coverage and the cost across the technologies presents new challenges. And while we were doing this, I think one question we kept asking ourselves was, hey, this is a planning problem. We're doing this a priori. So why not just run the entire thing in for optimal stuff? And I think Tumchun went through some exercises, and I don't know if you have a slide on that, Tumchun, but the amount of time can be significantly large as you start increasing the number of options. And so I think to make this meaningful as a tool for an urban planner, reducing the number of locations where you could place was a very big help.
I can imagine. I have one more question. I'm going to give Tumchun a chance to end. So you presented two very nice examples, but I have another question. Did you try to present your system with a specification that was too constrained, and what happened? What would happen if you did that?
So I didn't get too constrained.
So that was overly constrained, that there's not a good solution. There's not a solution that can be met. Would your solution actually, would your system be able to actually tell the urban planner why it could not be met?
Right now we don't have that. That is a good question. So right now we assume right now the input we have all the input have an output of it, but we haven't tried yet. But I think that's a good direction we can try in the future.
It'd be interesting to know what kind of feedback that you could give to the urban planner based on the if you fail, especially.
Yeah.
Okay.
Sure.
Thank you very much.
Thank you.
Okay, let's move on. You can go ahead and stop sharing your screen. The next presenter is Corey Dai. He is a PhD student in Chengyang Lu's lab at Washington University in St. Louis, Missouri. His research topic is about mobile health and AI for healthcare. And he's gonna present some work where they actually had real doctors, my understanding, who were involved in the study and had real users who were studying. He's going to present live. Corey, the floor is yours. I can see your slides, but I can't hear you. Can we try again?
Yeah, can you say that again?
Yes,
Yeah.
and now I can see you. Great.
Sorry about that.
No, go ahead.
Yeah, so let me start. So hi everyone, my name is Rachel Dai. So it is my honor to present our work in IoTDI. The name of our work is the Respiratory Watch, measuring respiratory rate with a commercial smartwatch. So the respiratory rate is closely related to our health. It is not only an important indicator of some disease like sleep apnea, but also used to assess sleep quality and detect stress level, even opiate overdose. However, traditional R measurements is burdensome, which is usually limited by the special equipment like the respiratory belt and or gas mask. It is not suitable for an obtrusive and long-term monitoring in our daily life. So, as you know, nowadays with the technology advancements, the smartwatch has gained tremendous popularity in our daily life. There are multiple sensors on the smartwatch, including the inertial management to measure the motions or activities, and the PPG sensor to measure the heart rate. The popularity and the sensors enable us the long-term and obtrusive health monitoring. So, can we measure the respiratory rate with our smartwatches? The answer is yes. Previously, researchers have tried to use IMU sensors to measure the respiratory rate, which captures the micro motions of our respirations. This usually works in conditions with limited motions, and it is greatly vulnerable to the sensor noise and motion artifacts, thus making it not suitable in our daily life with the motions. So remember that in our smartwatch, we also have the PPG sensor. So can we measure the respiratory rate with the smartwatch PPG in our daily life? Yeah, the PPG sensor is an optical sensor to measure the blood volume changes. There are two types of the PPG sensor. One is the transmission mode, which is usually used in the fingertip PPG. As you can see here, it has an LED and a photodiode. The LED emits light through our vessels, and the photodiode measures the light changes. Then we translate the light changes to our blood volume changes. Similarly, the transmission mode, the reflectance mode also has an LED and the photodiode, but it measures the reflected light through our vessel. The reflectance mode is usually used in our smartwatch or wristband. The PPG sensors are majorly used to measure the heart rate. However, there are also some modulations from the respirations in the PPG waveform. As you can see here, it modulates the PPG in three ways: frequency, amplitude, and intensity. The frequency modulation is shown as the brown lines. Basically, you can see here, the respiration process changes the peak intervals between the consecutive peaks of our heart rate. The second is the intensity modulation. As you can see, the purple curve here, basically our respiration process will change the baseline render of the peak. You can see here, there are some different peak absolute heights about the PPG waveform. The third modulation is the amplitude modulation. As you can see here, the lives here. Basically, our respiration process will also change the height of the peak to value distances. So as you can see here, the peak positions of the PPG waveform are critical to extract these modulations. Once we can extract these modulations, then based on these modulations, we can estimate our respiratory rate from these waveforms. So that's the basic idea of how we can estimate the respiratory rate from the PPG waveform. However, there are still several challenges. First, there are significant noise and motions in daily life. And the PPG, the smartwatch PPG has lower signal quality than the fingertip PPG. We need a robust pipeline to handle the signal. Second, for real-time and long-term monitoring, we need to leverage both accuracy and yield of the respiration measurements. Third, the smartwatch is a constrained platform with limited resources and battery. Our approach needs to be very efficient to be run on the smartwatch. To solve these challenges, we have proposed our wristwatch applications that can directly run on the commercial smartwatch. Basically, we first tried to separate the approach to estimate from the smartwatch. The first one is the signal processing estimator, which is highly efficient and shows high accuracy in the presence of low noise. The second is the deep learning estimator, which shows robustness with the significant noise. And the third, based on the signal processing and this deep learning, we further propose the hybrid estimator, which can leverage the complementary advantages of the signal processing and deep learning. It shows high accuracy under the moderate noise as well. It also shows the robustness to significant noise, and it has moderate efficient combined the signal processing and the deep learning estimator. So let's first look at our signal processing estimator to measure the respiratory rate. For the signal processing estimator, we have 3 stages. In the pre-processing stage, we divide the signals into 6 seconds windows and resample the data to a fixed sampling rate. Then we apply the bandpass filter to filter out the noise band beyond the heart and the respiration bands. Then we have the artifact elimination and pulse peak finding stage. This is the stage we implemented the fine-grained noise artifacts elimination techniques. Basically, we used a sliding sub-window technique and a PPG pattern detector within it. The second stage, in the second stage, we calculate the respiratory rate and the estimation quality index from the last stage. So let's zoom into our second stage. We majorly utilize the PPG pattern detectors for each sub-window, and we have our sliding sub-window approach has a window size of 10 seconds and a step size of 2 seconds. After each sub-window is passed into the PPG pattern detector, and here is the example of the waveform, PPG waveform of the sub-window. As you can see here, the blue curve is the unfiltered PPG waveform. It is hard to find the pulse peaks, and it also is hard to classify whether this blue curve is a valid PPG or signal or not. So we applied a forward-backward filter on the blue curve. As you can see here, the green curves here is the waveform after a forward-backward filter. After the filtering, we can see we have the clear hard-beat patterns. It's easy for us to find the pulse peaks, and so that we can classify whether it is valid PPG sensor or not. Compared to the traditional filters, as you can see here, the traditional filters has various shifts of the PPG peaks after the filtering. We cannot map the peaks after the traditional filter back to the original PPG waveform. So that's the advantages of our forward-backward filter. We can map the peaks back to the original PPG waveform. Why do we need that? Remember that the peak positions of the PPG waveform is the key to the respiration estimation. We need to find the pulse peaks the original waveform to extract the respiration modulations, then we can estimate the respiratory rate. So here is the example of the after filtering, how we detect whether it is valid or not. As you can see here, after the full battle filtering, the PPG waveform becomes more clear, and it has clear patterns of the heartbeats. And here is another example of an invalid PPG waveforms after the full battle filtering. As you can see here, the peak height varies a great bit, and the peak distance is also varies great bits. So we classify this is an invalid sub-window. We use decision tree classifiers in this stage for the PPG pattern detector. So after detect where each sub-window is a valid sub-window or invalid sub-windows, we only keep the peaks in the valid sub-windows, like here. These peaks are kept, and the noise peaks are eliminated. So this helps us to achieve the fine-grained noise elimination. Then with these peaks, we fed into the third stage. We fed this peak into the third stage. We construct the respiration signals based on these peaks, and we use adaptive peak findings to estimate the respiratory rate. So besides, we also proposed the novel estimation quality index, DEQI. DEQI is used to assess how accurate our measurement it is. It is important to trade off between the accuracy and the yield. Prior studies use the motions to estimate the accuracy. Basically, if there is a higher motion intensity, then the measurement should be less accurate. However, this approach relies on another motion sensor. We propose the EQI, which does not need other sensors, and it can capture not only the motions but also other impacts. It is based on the two assumptions. Basically, first, the respiration process is rhythmic. We can assume that the peak intervals of our respiratory rate, the standard deviations of the peak intervals of our respiration waveform should be small. And the second assumption is that the longer sequence we have, then the more accurate measurements we have, as you can see here. So then this EQI not only help us to estimate the accuracy of our measurements, we will then also use this into our hybrid estimators as the bridge. So after a look at the signal processing estimator, let's look at our deep learning estimator. So deep learning is reported to be robust to some noise with a smartwatch sensor. So based on this idea, we have built our our deep learning estimator. It can directly output the respiratory rate from the smartwatch sensors. Similar to the signal processing, we first have the pre-processing stage. Then we have an actual standardization process after the signal processing stages, the processing steps. Then after that, we put the pre-processed data into a deep residual network. We changed the original 2D convolutions to 1D convolutions because our PPG waveform is only one dimension from the sensor. Also, we changed the classification problems to regression problems because we want to directly output the continuous respiratory rate measurements. For detailed information about our deep learning estimator, please look at our paper. Yeah. So that's the deep learning estimator. In our experiment, we have found that the deep learning is very robust to the significant noise. So we further proposed a hybrid estimator, which can leverage the complementary advantages from the signal processing and the deep learning. And let's look at our hybrid estimator. We want our hybrid estimators to dynamic switch between the signal processing and the deep learning. So how to switch between the two basic estimators? The EQI, the estimation quality index is the bridge. Basically, here is a diagram of our hybrid approach. Basically, if the EQI is less than a threshold, we will use the signal processing estimators as the output. If the EQI is greater than the threshold, we will use the deep learning estimator as the output. And this EQI helps us to dynamically switch between the deep learning and the signal processing, so that we can utilize both advantages from the two base estimators. To evaluate our approaches, we have conducted a user study. So we use a commercial smartwatch running on a Google Wear OS system, and we use a raspberry belt to collect the respiration ground truth to validate our measurements from the smartwatch. And in our experiment, we have included serious activities, including the free written and serious activities, including the speech, math, and free living tasks. We have included 32 participants into our study. So let's have a first look about the activities impact on our estimation accuracy. Here is one example from one user. We plot his estimations during the whole process, as you can see here, from the video period to the speech, math, and code, and free time, including some free times and our final video period. And the top graph shows the motion intensities of the respiration shows the motion intensities during the whole study. So let's look at the first video period. As you can see here, during the video period, the blue curve here marks the ground truth of from our respiratory belt, and the diamond marks the outputs from our signal processing estimator, and the black plus marks the output from the deep learning. So as you can see here, in the video period, we have our signal processing estimator that's more closer than the ground truth. This shows that the signal processing is more accurate when the motion intensity is less. But when we look at when there is more motions, as you can see here, there is more motions than the video period. The deep learning shows more accuracy than the signal processing. As you can see here, there are large variance of the signal processing estimators. You can see here the red diamond marks here. So this first look gives us information that the signal processing is more accurate during low motions, and the deep learning is more accurate than the during the when there is higher motions. So let's look at our detail in evaluation process. So here is the accuracy in evaluation. We use the mean absolute error as the metric. We have implemented 3 baselines. Since this baseline don't have the noise elimination techniques in our approach, so in the original work they just discard the signals with the noise. So here they cannot handle the noise within a data window. So here, as you can see here, the 3 dots marks the baselines. It can only have less than 20% yield in our data set. For the accuracy of our measures, we sort the data based on the EQI to show the trade-off between the accuracy and the yield. So basically, from left to right, we have increasing EQI to cover more and more data, so that the yield is also increasing. As you can see here, when we only cover small fractions of the lower EQI, we have the lower yield. And as you can see here, this matches that our signal processing, as you can see here, the black curve is has much smaller mean absolute error than deep learning, as you can see here. But when we cover more and more data with a higher EQI, as you can see here, the signal processing quickly has worse performance than the deep learning. So as you can see here, and here the green curve it shows our hybrid approach. It can dynamically select the deep learning and the signal processing. So as you can see here, the green curve has the lowest overall mean absolute error at the yield of 100%. And this shows that even when the EQI is small, we can cover less of the data. As you can see here, the EQI is directly use the outputs from the signal processing, so that you can achieve the low error during for the whole process when covering all the data. Besides, we also implement our Raspberry Watch, including the 3 estimators in a commercial smartwatch. So we have used 2 commercial smartwatches as listed here. The running time are listed as here. As you can see here, our signal processing running time is very, very efficient. It runs less. The running time is less than 15 milliseconds. But for the deep learning running time, it needs more than 6 seconds to run. So as you can see here, this also highlights all the advantage of our hybrid estimator. For the hybrid approach, the running time is around 3 seconds. So the hybrid approach balances the runtime and the robustness and accuracy for the signal processing and deep learning. So that's all for the 3 estimators. In conclusion, we have built the Raspberry Watch system on the commercial smartwatch to support robust respiratory rate monitoring. We have explored the trade-off between the efficiency and the robustness against the noise. The signal processing is highly efficient and it has high accuracy and moderate noise. The deep learning is heavy weight, but it shows robustness under significant noise. Our hybrid approach can combine the efficiency and robustness. Empirical evaluations shows that the feasibility of running Raspberry Watch on the commercial smartwatch. So that's all for my talk. So thank you. Any questions, welcome.
Okay, thank you, Corey, for a nice talk. It was nice and clear, and it's nice to see that you actually implemented the system and tried it out with real people. Ziki Wang has a couple of questions for you. Can you unmute your microphone?
Sorry. Let me see it.
Thank you, Dr. Murphy. Yeah, I have actually 2 questions. So firstly, I was wondering, you might explain a little bit more about what are the factors that are going to affect the EQI index? I thought it's important when you are switching different models.
Yeah, so one moment, let's come back to the EQI. So remember that previously the researchers have using the motion sensors to estimate the accuracy. Basically, if there is a higher motion, then the measurements could be less accurate. But in our experiments, we propose the EQI. Actually, this doesn't lead to a larger sensor, and actually our EQI is calculated from the signal processing estimator itself. Basically, we use some characteristics from the measurements. So here is the modulations from the signal processing. Basically, let's look at the RIIV, the intensity modulation as an example. As you can see here, there is variations of the peak heights. So basically, for the blue curve from peak to value, actually it matches one respiration cycle. Yeah, we can assume that the peak matches the inhaling of our respiration, and the value matches the exhaling of the respirations. So basically, we can calculate the peaks of the RIIV, as you can see here, the peaks. So we use the peaks informations to as our EQI measurements. So basically, if the peak intervals between the RIIV has a small standard deviation, then we know that it is rhythmic and it matches the respiration. So in that sense, we see that this measurement is accurate because it matches our respiration process, and our respiration process is also rhythmic, so that we have small standard deviation of the peak intervals. And the second assumption is that the longer sequence we have, the more accurate the measurement it is. And this is shown in the previous literature. And in our paper, we also shows that we have results show that the longer sequence we have, the more accurate we have in the original paper. So based on these two assumptions, and these two assumptions to measurement is from the signal processing estimator itself, from the signal quality itself, so that we can use this to estimate the accuracy of our measurements. So it does not use any other sensors.
That makes a lot of sense, actually. A second question would be also in this page, like your goal is to trade off accuracy and yield. You might actually define the yield a bit more?
Yeah, that's a good question. So basically, as you can remember that we have collected the 32 participants user data. So we see all the user data. If we can estimate all the data for all the 32 participants, then for the respiratory rate measurements, then we see that is 100% yield. But sometimes when there is increasing noise, we have to draw parts of the signals, because there is low measured information in the signal. We have to drop some of the meaningless data, so that we have lower yield. In that case, we have to drop some of those measurements. So as you can see here, for the signal processing estimator, actually it only has the yield of 86%. This means that for the whole data set, it drops about 14% of the data. It cannot measure the respiratory rate from that part of the data. Yeah. So in our real case, in our real usage, we want to have the accurate measurements in our smartwatch, because only the accurate measurements can help us to do the following analysis about some of the predictions about the respiratory disease or diseases. So in that sense, the EQI can help us to select the accurate measurements, so that if we only select a part of the measurements, then we have a lower yield.
I see. Thank you. And that was an excellent talk. Thank you so much.
Yep, thank you for the questions. Chris, do you have questions?
Yes, I do. Thank you, Dr. Murphy. Rayshwan, this was a really cool talk. I really enjoyed it. I think this type of a data-driven approach is going to prove to be very valuable for IoT moving forward in the future. I guess my question is twofold. One, did you explore different types of neural network architectures that you could have run that would have been lighter weight on the watch?
Yeah, that's a very good question. So at the current stage, we just use the ResNet, and we just simplified it a bit. So for future work, we will explore more architectures of the neural network. At the current stage, we have tried different architectures, but the ResNet shows best performance. And in the future, I think we can even improve the performance. For example, we can use the quantizations of our neural network to let it more suitable run on the smartwatch. Currently, the running time is still kind of high, as you can see here. It still needs to 6 seconds to run the deep learning. Yeah, that's quite larger than the signal processing. So I think in the future we have to implement it.
It's really important, because if you can get the deep learning running time down, you could actually integrate these into one continuous model, rather than sort of thinking about them as two separate models, right? There was a edge computing paper called FlexDNN that begins to explore these problems with these data-driven approaches, I'd recommend. The second question, though, in this world where we have two different models, which I think is a fine world to be. Like I said, I really like this paper, thought about it quite deeply. Have you explored any rigorous guarantees for this online algorithm and how you're going about switching between the two models? I know you picked a threshold, but it wasn't clear to me if you had thought about maybe just online algorithms and what types of competitive guarantees your algorithm could give.
Yeah, actually, that's a very good question. So currently, our analysis is based on our data sets. So personally, no one has tried to use the commercial smartwatch to measure the respiratory rate directly and run the algorithms on the smartwatch. So I think that's also a lot of future steps we want to explore. Currently, the EQI, we select the EQI is based on the grid search. Basically, we just find the best here. It's an offline analysis. So I think in the future, maybe when we trying to do the smartwatch applications for each user, first we can have a calibration process. So for the calibration process, we can select the best switch point for each subject.
Okay. Thank you.
Okay, that's about as much time as we have. Thank everybody for asking the questions, and thank you all for the great presentations. This was a great session. Thanks you all. Thanks a lot. And I guess now there's time for a break.
Thank you.
Bye-bye.
Thank you.
Thank you all. The next session will be 1 p.m. according to Central Daytime. It is session 9, networking.
Amy, are you still around?
Yeah, I am, although my family is asking me to come for dinner, so I don't have much time.
Oh, that is okay. I wanted to share with you, hey, it's a pleasure to meet you.
Yeah, it is. It is nice to see.
You probably
to the name.
don't know this. You probably don't know this, but at one point in time, I dreamt of being your student.
No.
So I am a U of R grad. I came the year after you left, and so I ended up being Kai's student.
I was going to ask, who did you work with? Kai is a great person. How is he doing?
He's doing, I guess, well. I haven't. I'm pretty long since graduated, right? Because I guess.
Come on, I know how my advisor is doing, and that was 21 years ago that I graduated. Come on. You should tell Kai. You should tell Kai I told him to get you to get in touch with him.
I mean, he's still publishing like crazy and doing stuff that makes me say, wow. So I guess he's doing well. But yeah, I thought that was interesting. When I saw your name, I was like, oh, wow, I finally get to meet her because.
No, I'm sorry. I have this great family here in Italy, so I don't regret my choice in leaving at all. But
that's okay. I didn't expect that. But it is a pleasure to meet you, and crazy that we would end up working on the same conference together in the end.
It's funny. I'm glad you reached out to the other people in the organizing committee to chair the sessions, because you ended up with a lot more sessions than I think people normally do, because you only put 2 papers in them. So you had quite the task to match everybody up.
In the end, I think it worked out having longer sessions and longer question answer time. Once the first one was a little rough because people were afraid to ask questions, but I've noticed the questions have been pretty good. I won't keep you any longer. I just wanted to meet you.
Yeah, it was nice to meet you. I hope to meet you in person someday. Okay, bye-bye.
All right, everyone, we'll give maybe just one more minute for people to arrive. It's good to see that virtual conferences have the same issue with attendance on the last day as real conferences. I'm sure everybody is waiting to get the videos on recording as we would do in a live conference, even if we're not, on flights headed home early or whatever it may be. In physical settings. Alrighty. Do you want to go ahead and share your screen, Mehdi?
Hi, sure. Can you see my screen?
Yes.
Great.
Alrighty. I will start here just 1 minute late. That's perfect. We'll have time to go over. So everyone, welcome to our last session for IoTDI 2021. I hope the talks have been as engaging and exciting for you as they have been for me. Our last session is generally described as networking, but really, obviously, that's a broad term that covers a wide range of topics. Our first presenter is Medhi Jafarzadeh, who received his PhD from McMaster University in Canada just last year, working with Rongzheng. He is currently working as a wireless developer in ZenReach. He's going to talk to us today about SoftBL, a SDN framework for BLE networks.
Okay, thank you. Yeah, as you said, I'm Mehdi Jafarizadeh, and this paper is by me and one of my colleagues, Xingji Liu, and my supervisor, Rang Zheng. And today I'm going to present a research about a software-defined networking or SDN-based framework for BLE-based IoT networks. It's called SoftBL. So let's begin with an example to illustrate the problem. Assume that you want to monitor the temperature of different spots in a data center, where the sensors are installed in front and back of each server. Such a monitoring network can contain up to 100 sensors per meter cube, and the whole network can contain thousands of sensors. Can we develop a reliable and low power transmission protocol for such a dense network? So when we are talking about low power, Bluetooth Low Energy or BLE becomes a good candidate. So the main objective of this research is a reliable BLE-based dense monitoring network. But is data center is the only example of dense monitoring application? No, it's one of the many different IoT applications that need that dense monitoring. We have dense monitoring applications in agriculture, and industrial plants, and in smart buildings and cities. So other than being reliable, our network should also be adaptable to different network topologies and different application requirements. And why BLE? Because it is one of the most power efficient edge protocols compared to other edge protocols like Zigbee or LoRaWAN. It is slightly more power efficient. Also, there's a new controllable parameter in the recent SDK of BLE devices, which is channel map. So we can adjust the advertising channel map and scanning channel map, unlike the, for example, 3 or 4 years ago, that those channel maps was fixed for 3 channels. We can now manage those channel maps. So it also motivated us to have this channel assignment or channel management in our network. But is this the only BLE-based sensor network or IoT network? No. We had other networks. Some of them were based on BLE connections. But we have, in these networks, we have connection overhead. And the BLE connections are going to be terminated unexpectedly. We have another solution, BLE mesh, but it has been proven in other work that it's not scalable for a network of more than 100 sensors. Also, we have a new feature called periodic advertising. It was introduced with BLE5, but it has not implemented widely by all the vendors yet. So we chose legacy advertising in BLE because it has been implemented by all the BLE vendors on the BLE devices, but it is not reliable nor adaptable. So we have three problems. We need to solve. We need to address three problems before applying this legacy advertising in our network. First, BLE has a high bit error rate in legacy advertising. Almost 10% of the packets are lost when the receive signal strength is below -80 dBm. So we need to develop an architecture that relieves this unreliability in packet advertising. Second, unlike ZigBee, where nodes are orchestrated by coordinator, or LoRaWAN, where the network is controlled by a network server, BLE doesn't provide any built-in module for controllability. So this means that we need an overlaid framework to provide network adaptability. And third, if we have sensor nodes controllable, how we should find the optimal values for the parameters. So our solution is called SoftBLE. In a nutshell, it has a two-tier architecture. It features software-defined networking or SDN-based framework for adaptability. And it proposed two orchestration algorithms for channel and TX power assignment. Let's take a look at the network architecture. So as we said, SoftBLE is a two-tier network. Let's go back to our data center monitoring example. In this architecture, the sensors send their data through BLE advertisement to some gateways that in data centers are installed on top of the racks. And the gateways forward them to a central controller via a reliable link or like TCP over Wi-Fi. This hierarchical architecture is duty cycled and enhanced by multi-gateway packet reception. Also, the data is sent through scannable advertising packets, which is acknowledged by scan request. This acknowledgement mechanism, beside the multi-gateway packet reception, help us to overcome the high bit error rate of BLE. Let's take a brief look at the BLE protocol in the first tier. In leak layer of BLE, a device can have 5 different states. In SoftBLE, the gateways are always in a scanning state, but the sensors wake up in advertising state, and at the beginning of every duty cycle, they advertise their data, and after that, they go to sleeping or standby state. We omit the overhead of connection state in data transmission. However, we will see that the connections are used in SoftBLE to transmit the downstream control commands. A BLE advertiser, by default, advertises normal and non-connectable packet. In this mode, if the packet is lost, there is no way to inform the advertiser about it. So this timeline is showing the duty cycle normal, non-connectable advertisement. But in SoftBLE, we are using an scannable advertising. And the sensor, after each advertisement, it waits for a scan request as an acknowledgement to receive. So if a transmission is failed, like here in this scenario, it retransmits until the sensor receives an acknowledgement, or in BLE we call it a scan request. It retries until the number of retransmissions hits a upper bound threshold. In our case, we set it into 3. We retry 3 times. So let's take a look at the adaptability framework of SoftBLE. We have seen the architecture, and now we are ready to see how we can make SoftBLE adaptable to different topologies and application requirements. First, please note that BLE is a parametric protocol. We can parameterize the advertising, the scanning, and the connection of a BLE transmission. As I said, we don't have connection state in BLE data transmission, so we skip the connection parameters. But through the advertising parameters, we optimize the channel map and the TX power on the sensors and use the addressing parameter for sensor to gateway assignment. On the other hand, we optimize the scanning channel map on the gateways, and again, we utilize whitelist for sensor to gateway assignment. So channel maps on both gateways and sensors are going to be optimized, and addressing on the sensor side and whitelist on the gateway side is going to be used for gateway to sensor assignment. So in total, we have 5 different parameters as control maps. But how we can adapt these parameters on a network node? By adaptability, we mean the ability to control and optimize the network parameters according to topology and application requirements. So the first required network, this first requires network controllability, and second requires decision-making algorithms. Our solution is a software-defined networking-based overlaid framework in which the networks as the end users, the sensors as the end users, and the BLE gateways as the SDN switches are controlled by a detached central controller. The framework has 3 main parties. First, the controller, the gateway, and the sensors. We talked about the forwarding plane, that the sensors collect measurements and send them to the controller through BLE gateways. But in SoftBLE, we add an overlaid control plane on top of that, which include 3 stages: provisioning, orchestrating gateways, and orchestrating sensors. First, sensors send provisioning requests to join the network. Based on the received signal strengths of these packets, the controller built an observation matrix, which is the main input of the orchestration algorithm in the next stage. Then the controller decides about the scanning channel of each gateway and send it through a reliable link. In the third stage, the controller decides about the advertising channel and TX power of each sensor and disseminate them to the sensors through BLE connections established by the gateways. At the end, we have a substitution. The MAC address of each sensor is replaced by a random address in gateway's memory. So this address is the same for all the sensors that are assigned to the same gateway. It's due to the limited capacity of whitelist in BLE device. We have only, in the current BLE devices, we have only 8 spots, so we cannot define a different address for each sensor. And this was the STM framework. And let's take a look at the orchestration algorithms for channel management and for the TX power optimization. Along with soft BLE framework, we also propose two orchestration algorithms. The first one is for scanning channel assignment on the gateways using a heuristic that solves minimum interference frequency assignment problem, or MIFAP. The proposed heuristic is iterative. In each iteration, we have the gateways that has the maximum overlap sensors with the already colored gateways is selected as a candidate. Then the candidate gateway is colored with a channel that causes least sensor overlap with the gateways that are already assigned to the channel. The second orchestration algorithm is for the sensors. It is pretty straightforward. We have 13 possibilities for TX power and 7 for channel assignment. So 91 options in total. Among them, we select the one that results in the least estimated power consumption while satisfying the PRR threshold of the application. The power and the power and packet reception rate that these are estimated using a similar analytical model that we have proposed in our previous work with a little bit modification. So in this figure, you can see that we have a candidate with it satisfies the estimated packet reception rate. So it is below the threshold of packet error rate, and it has the minimum expected power consumption. So star here means 3 channel. We are going to select this star, sending on all 3 channels. And the color shows in this color bar that how much is the TX power. Here is an example result of running the orchestration algorithms. The network is 50 by 50 grid of sensors covered by 11 by 11 grid of gateways. You can see that gateways are not perfectly colored. I mean, there are some cases that the neighbor gateways have same colors or assigned to same channels, like, for example, here, these 2 red gateways. Oh, sorry, these 2 red gateways. The reason is that we only have 3 channels to assign, which is not enough for a perfect assignment in large scale. Let's take a look at the performance evaluation results. We evaluated soft BLE and compared it to Lemonet, which is a similar 2-tier BLE-based network architecture, but not adaptable. Lemonet has two types of nodes, like NCL and SCL. NCL is normal connectable and SCL is scannable. You can see here that using soft BLE, the sensor power consumption declines 70% compared to our benchmark Lemonet, and the packet reception rate is kept over 99.9% in almost all the sensors. And also, we also conducted a large-scale simulation, and the network includes 1,000 sensors covered by 33 gateways in 2,500 meter square area. You can see in the plot that soft BLE's utilization is 3 times higher than Lemonet. Also, it performs better than both NCL and SCL nodes of Lemonet in power consumption. So as a conclusion, soft BLE provides a reliable architecture for dense monitoring network, an SDN-based framework to control the BLE parameters, and the channel and TX power orchestration algorithms for BLE. Also, soft BLE can we adapted to different network topologies. It almost guarantees the application required packet reception rate, while it can reduce the TX power consumption of sensor nodes by 60 to 70% compared to similar static architectures. Thank you.
Thank you, Mehdi. Any questions from the audience? Would anyone like to start? I definitely have some questions, but. All right, so I'll get it started. I think, so maybe the most simple is, what about failures of sensors and some of those types of just reliability issues? Can SoftBLE handle that? And is that in future work?
Yeah, that's a good question. In this diagram, you can see that we have the framework to control the sensors. So far, we have introduced only channel assignment and TX power management. Based on this TX power management is based on the provision request that we have collected. But we can extend this. So instead of only collecting the provision requests and run these two algorithms, we can extend this framework easily into the running time. So right now we are going to decide everything at the initial step, at the provisioning stage. But we can extend it to running time, and after provisioning, if any failure happens in any of the sensors, we can establish some policies like alert somewhere, alarm somewhere, or filter out, or we can filter out that sensor from the final data and try to extract the data, interpolated data of that sensor based on the neighbor devices. So we have that capability in this framework, but yes, in the only algorithms that has been implemented is for channel and TX.
Well, and I think you're hitting on what my second question or second suggestion for future work was going to be, which would be to make it data-driven, right? Because you talked about this mechanism to improve the bit rate, to reduce lost packets, of resending a set number of times. You said specifically 3, but obviously it's a parameter. But it seemed to me like that would be a straw solution, in the sense that some sensors are likely to have much more valuable data than other sensors, right? In particular, in the data center example, I can imagine that sensors that are operating near the center of the data center versus those operating near the aisles, which are cooler, are going to be much more valuable. You just need to know what those temperatures are in order to adjust your AC or whatever it is that you're trying to do. So have you given any thought to sort of what SoftBLE looks like when you're using, making these adjustments based on the data that's being sensed, right? Based on things from the data plane, rather than just things from the software implementation and the network side.
Yeah, it's a correct point that the sensors has different importance level of data. The application we left right now that level of importance to the application level requirements. So the application can define for us that I need some of my sensors that, for example, are in the cold aisle, or some of the sensors that are in hot aisle to be, in hot aisle is more important, in hot aisle to be monitored more frequent than the sensors that are in the cold aisle, for example. This is defined by the application. So right now we are defining only the duty cycle to be the same for all the sensors. But yes, but yes, you're right. If the sensors have different duty cycles, the framework can handle it. If they have different requirements, for example, we have a packet reception rate threshold. This is the input-out model. This packet reception rate threshold could be different from sensor to sensor, so some of them can send with higher TX power to overcome this packet reception rate requirement, but some of them that has less requirement can send with less TX power. So both duty cycle and packet reception rate, they are going to be defined by the application layer, and we have that capability in this framework to mitigate them.
Yeah, I really like that aspect. And I like this as an initial paper, right? Because you described other applications beyond the data center. But as we begin to move toward a data-driven solution here, right, you're going to need just the characteristics of the data center to really optimize those parameters, like you were just saying. You know, there was, and I actually love the application of the data center. That's maybe my original research calling area. There's a paper in ISCA this year from Beyond Keeney's group at Microsoft that is looking at a very similar problem, right? So managing the HVAC systems with water-cooled data centers that probably could use a framework just like this. So it's a reference. Any other questions?
Is it possible I make a comment?
Yes, yes, of course.
This is Ron Sen from my Master University. By the way, it's really good question that you asked. I just want to kind of follow up the response from Mahadi. So I think what self-BLE enable really is number one. If you think about it, you have SDN controlled network. You need to have the ability to be able to send your command and control reliably. That's something that this framework facilitates. Number two, on the device side, you need to have the interface and the right tuning knobs that you can change. To some extent, we have to export multiple control parameters on the sensors. So the two orchestration algorithms are actually demonstration of the capability. Like when you talk about a data-driven based control decision, this can be facilitated by the framework. The question is more like because we're thinking in the SDN sense that it's going to be logically centralized. So how the decision made, whether it's we would expect to be done on a centralized controller, whether it's data-driven or based on some optimization algorithm or some even just some software that pre-coded, that is sort of orthogonal to the framework per se. So you can take the data you have and make a decision and decide, okay, this sensor can have a lower duty cycle, or that sensor does not have to transmit over 3 orthogonal broadcasting channels, things like that. That level of decision can be done logically at the central controller. The important thing is that once you make the decision, the self-BLE framework can disseminate the command reliably, and you have an interface on the sensor to make such changes.
No disagreements from me, Ron.
Okay, that's why we can probably move it offline.
No, it's a very good points. I agree with everything you just said. All right, are there any other questions? All right, so we'll thank our speaker, and you can stop the share and allow the next speaker to come on. Okay, our next talk is from Omid. I'm sorry, I need you to explain how to pronounce your last name.
Tavalloi. I know it's a little bit difficult to pronounce.
I'm sorry. I should have asked beforehand. Amit is a fourth-year PhD candidate at the School of Computer Science at the University of Sydney. His research interest is in designing quality of service aware solutions for the communication of embedded devices based on optimization theories. In particular, he's currently working as a researcher in the Center for High Performance Computing to design time synchronization protocols for low power Internet of Things based IETF standards. In particular today, we're going to get a talk about 6G, mobile 6 networks. Go for it, Amit.
Thanks, Christopher. Hello, everyone. Welcome to my presentation. My name is Omid, and today I want to present our contribution DTSF, or Distributed Traffic Away Time Slotted Channel Hopping Scheduling for Low Power Mobile IoT Network. So in this presentation, first, I generally talk about the mechanism of time slotted channel hopping. And after that, I will show you why the current approaches and the state-of-the-art method do not have good performance under heavy traffic load or in the face of mobility. After that, I explain the mechanism we use for frequency allocation, time slot allocation in detail. And finally, I present the evaluation result and talk about how we implemented our contribution on real resource-limited device. Time slotted channel hopping introduced as a part of IEEE 802.15.4e as a mechanism that can be used in low power IoT networks to meet requirements of real-time applications. Based on a communication schedule, TSCH combines time synchronization with frequency channel hopping in order to cope with wireless interference and multipass fading. So in time slotted channel hopping, we slices the time into a group of time slot, which is called a slot frame. And each time slot has a duration of 10 milliseconds, which is enough for sending a packet to a one-hop neighbor and then receive an acknowledgement. Totally, by using 16 frequency channels, we distribute all communication in the network into a matrix that we call it CDU, or Channel Distribution Usage Matrix, with 2 dimensions, frequency and time slot offset. So this slide shows a simple example of CDU matrix, which is created based on the TSCH schedule, or time slotted channel hopping schedule. As you can see here, each cell is used for sending a packet to just a one-hop neighbor. For example, here, this cell is used on time slot 1 by using the frequency channel 2 for sending just one packet from node B to node A. And when we do not have any value in a cell like this, for a node like F, it means node F can stay in the sleep mode in this time slot. Since 2015, 60ISCH working group of IETF has been designing standards in order to integrate TSCH with the other standards, RFC standard designed for low power IoT networks such as RPL routing protocol. So 60ISCH has a sublayer that we call it 6-stop, and based on this 6-stop, low power IoT nodes can create a TSCH schedule and update it by using a scheduling function. So we can consider a scheduling function as a upper layer for the bandwidth adaptation technology that uses low-level services in order to map TSCH cells to one-hop neighbors. So node in low power IoT network use 6-bit transaction based on the 6-stop protocol, which is part of 60ISCH networks, in order to have negotiation for creating this schedule or updating. So based on the scheduling function, we can find when we can add or remove a cell from the CDU matrix. Or for example, for each node inside the topology, how many cells can we consider? Also, for a specific packet, when we send from node A to node B, we can find a unique cell in the CDU matrix, which is used for this transmission. Other IETF standards such as RFC 8180 or RFC 8480 stated before that designing dynamic scheduling functions currently are missing components in IETF standard and 6ISCH architecture that could be defined in the near future. So in order to explain why adopting the TSCH schedule or designing a dynamic TSCH schedule is challenging, I use an example in this slide. So in a network that you can see on the left side, we have mobile nodes such as node I that can change its preferred parent in the directed acyclic graph topology or DAG topology. For example, node I can move to the outside the communication range of node D to select node E as its preferred parent in the DAG topology. Or in other words, it can change the DAG topology. Based on this, we need to update this schedule. So if we consider the packet generation rate of node I as 1 packet per slot frame, when node I selects node E as its preferred parent, we need to remove this time slot with orange color, ID, and DB, and add 2 new cells into the CDU matrix with values IE and EB. The same case can happen when the noise around the node like node H increases. So node L may prefer to select node G as its preferred parent in this topology instead of node H. Based on this, we need to remove or update the TSI schedule by removing these cells with the value LH and HC, and then add 2 new cells, LG and GC. So in order to design a dynamic schedule, we need to consider mobility in the network. And we need to consider the change in traffic dynamics. To cope with these problems, in this paper, we propose distributed traffic aware scheduling function for time-slotted channel hopping. And in the design of our contribution, we consider having high queue backlog as an indication of congestion. So for the nodes with higher load, we try to assign them more TSCH cells. Also, by using a lightweight approach, we estimate mobility in an approach that doesn't use location information and hence can be run on a wide range of IoT modes with different hardware specification. So we try to utilize time-slotted channel hopping schedule by increasing the network lifetime when the traffic load is light. So we put nodes in the sleep mode more. And on the other hand, when the traffic load is heavy, we utilize network resources in order to improve the network throughput. Also, for the channel allocation, for the communication of a node with its parent in the DAG topology, we assign a channel which is unique in tree hop in a path from root to the leaves in the DAG topology. And at the end, we model the allocation of TSCH time slots to the nodes in the DAG topology as a mixed integer convex programming problem, which is solved based on Lagrange multipliers, KKT optimality conditions, and the branch and bound algorithm. So DTSF is completely compatible with the other standard designed by IETF for low power IoT networks. And in our experiments, first we integrated DTSF into the Contiki operating system, which is operating system designed for low power IoTs. So it can be easily added to the current protocol stack we have for 6CIFTH in order to provide adaptability in time-slotted channel. So for the channel allocation, we use two different channels on each node for communication with the parents and with the children. Also for the nodes with the same parents, we use different frequency channel in order to connect them to their children. So this is a result of running our channel allocation algorithm. And as you can see here, when we move from the root node of this DAG topology towards leaves, we use each channel just one time in tree hop. For example, F3 is used just one here. And in order to implement this policy and keep this uniqueness feature, we limit the number of children in the DAG topology by 5. And the reason behind that is that IEEE 802.15.4 defines 16 frequency channels, but usually on implementation, 8 of them are used with the least interference. Out of these 8, we use a fixed channel for broadcasting control packets, one channel for communication with the parent node, one channel with the children node, and the rest of it, which is 5, for the nodes which are placed 2 hop from the parent node. As an example, node A on the enhanced beacon messages informs B of the channel that B can use here for communication with A, and the channel that B can use for the communication with his children, E and E. So after that, for each child node of B, we use a unique again frequency channel. Based on this, we limit the number of children to 5 in order to implement this feature. And for allocating time slots in our schedule, we have some policies. First of all, we consider a fixed number of time slots for control packets. And the total number of time slots we reserve for packet forwarding is always higher than what we have for packet reception at a node in order to balance the node load. Moreover, after each time slot we have for packet reception, we have one time slot for forwarding packet in the schedule. We consider these rules because of the problem we can have if we allocate consecutive RX or reception time slot in the schedule. Just consider a case when the queue length, the maximum queue length is 4, and we have this TSCA schedule allocation. So after receiving 4 packets, the queue is completely full, and the node has to drop this packet that receive on time slot number 4. Based on this, after each reception time slot, we consider one time slot for packet forwarding in order to balance the node load. So generally, we can categorize time slot into 4 types. A share time slot, which is used by both parent and children for transmitting data packets. The broadcast time slots, which are used for sending control packets. Unicast time slot is reserved for the communication of 2 unique nodes for just sending 1 packet or transmitting 1 packet. And finally, we have a sleep time slot when a node prefers to turn off its radio transmitter in order to save energy resources, which is a really important issue in low power IoT networks. So this is an example of running DTSF time slot allocation. As you can see here, we have a fixed number for broadcast or shave time slot, for broadcast time slot, which is 3 here for all nodes. And if we consider A as the parent of B and C, after each time slot, when B is receiving a packet from node D, its children, we consider one time slot for forwarding this packet to node A. Based on this, we are balancing the load of node B in our schedule. In addition to this, for each node, we use 2 shared time slot as an extra time slot. So the reason that we consider 2 shared time slot is one time slot is shared between a node and its parents, and one time slot is shared between a node and its children. So we want to consider mobility in our scheduling process. Based on this, we need to estimate mobility. So we try to find what is the impact of mobility on changing the topology. Based on this, we use this simple equation, as you can see here. While gamma shows the number of times that a node changes its parent. So when the mobile nodes change the topology, first they need to change the preferred parent assigned to them. And after that, we consider the duration of time that a node kept the communication with the parent alive. So by reducing this amount of time, or by increasing the frequency of changing parent in the DAC topology, we consider higher mobility for a node. And in addition to this, in order to avoid congestion and balance the traffic load in the network, we're monitoring the queue of each node by using exponential weighted moving average, which is a metric resilient against sudden change in the queue of each node. So for sending these values, we just add 4 bytes to the DIO packets, which are control packets used for creating a DAC topology as a part of RPL standard. And then we define a utility function, which is a logarithmic function based on the queue metric and mobility metric. So then we can define allocating time slot at the parent node to its children as an optimization problem, mixed integer convex optimization problem, as you can see here, while we want to maximize the utility of all children nodes. So as you can see here, for all children of node I, we want to maximize their utility. Based on this condition, we want to keep the forwarding rate of all children less than the receiving rate of the parent node. And since we can just one time slot, not half of a time slot to a node, we call this mixed integer convex programming problem. That means at the end, the result of optimization must be an integer value. So by using Lagrange multipliers and KKT optimality conditions, we can solve this problem and get the result that you can see on slide 22 and 23. And whatever we have here can be calculated just based on the mobility metric, Q metric, and for example, the length of the neighbor set of the parent node. But after that, we need to find the integer value. So at the beginning, we relax the integrality condition and just solve the convex optimization problem. But after that, we use a branch and bound algorithm in order to find the optimal integer answer. For example, if we find a value 6.5 for just one neighbor, one children, we add two branches on the binary tree for the values higher than 7 or less than 6, and solve the convex optimization problem again. until we reach a value which is integer for all children node, and it would be the maximum. So in order to evaluate the performance, we implemented on Zolarita Firefly IoT nodes that has the resource limitation, like they use just 32 kilobyte of RAM, which is even less than 1 megabyte. And it's really challenging. You implement an optimal solution on this resource limitation, and also integrated on the quantity operating system. So this is the result when we change the traffic loads. Orchestra is one of the state-of-the-art methods, published initially in Census in 2016, and even today is considered one of the best scheduling function. When the traffic load is less than 40 packets per minute, the PDR is higher than 90%. Orchestra can deliver 99%. But when we increase it after 60 packets per minute, its performance decreased to around 60%. While our contribution can keep its performance higher than 90%. And even if for the end-to-end delay, the difference is around 100 milliseconds, as you can see here. So in addition to this, we changed the size of the slot frame to be sure it can work fine. And again, for the Q loss, under mobility, when the Q loss of Orchestra is 700 packets per hour, the performance or our contributions around 220. And at the end, we change the slot frame length. As you can see here, the difference for the radio duty cycle is around just 3%. So in conclusion, while considering the queue backlog and node mobility, we design DTSF, and we model allocating time slot as a mixed integer convex programming problem. And the results show that we can improve the performance in terms of PDR and end-to-end delay significantly. Thanks for your attention.
Let's thank our speaker. Thank you, Amit. Questions? Someone want to lead off? So I actually only have one question comment on this. I appreciate the dynamic scheduling framework that you proposed here. It's sort of like my questions with the last talk. It seems like, well, maybe I'll ask a leading question first. Mm-hmm. Is the general goal here to provide high throughput and low packet loss for all? I guess you're thinking of it as nodes. I actually see it as pairs of communications equally in this particular framework, in particular in your optimization problem. I'm assuming a loss anywhere in the network is equal right now.
That's right. Yep.
Right. Yeah, building on that, I think there is, again, opportunity for data-driven approaches, right? What I really thought about when I was looking at the scheduling problem was the data center domain, and a lot of the work, tiny flow, for instance, or elephant and mice flows, where once you know what the weights between particular pairwise combination are, how important those messages are, and where you can afford the packet loss, you can maybe go into different types of scheduling techniques that could be online. So I guess that's a comment. If you want to respond to that, or
yeah, of course. So since we designed this based on the IETF standard or RFC standard that we currently have, they don't consider this, because all of this is just a general framework for IoT communication, and you can customize them based on your application. And what does it mean? For example, in the model that I have here on the utility function, we are just considering the queue length and the mobility. You can just add a weighting factor which is tuned based on the priority of the node in the network or based on the priority of the application node is running. In a lots of smart building application, it's like we do not prioritize the data because, for example, when we want to estimate the temperature inside the factory, doesn't matter where the node is placed. On any place, if we detect a fire, it's really important. We need to send it and deliver it to the destination. And again, for even this requirement, we have an IETF requirement standards. So first they describe, this is the requirement we consider for a smart city and smart buildings. And based on this, we just give you a general solution that you can customize it. Or for example, considering a weighting factor, which is directly related to the priority of application or node in the network.
Yeah, I get that. I mean, I do think that the range of potential solutions and the quality of the solution can vary substantially if I know more about the data source itself, right? So yes, I can add in the weighting factor, and that provides a very general way to adapt to workloads. But you know, I think more opportunities open up there. In particular, I would imagine on the reliability side, right? Because even now, it looks like with your framework here, you're still incurring under high load about 1 in 10 packets lost, which, as you said, for a fire may not be okay, right?
That's
now,
right.
one would say, why would I put that type of load on a network for sensing fires? But you know, again, this is where the data traces and something very specific to the workload to reduce costs and manage this may be very relevant. Are there any other questions or feedback? If not, I think that we will actually end on time. So everyone, on behalf of Valerie, Haiying, myself, and Tao, as well as our organizing committee, we would like to thank everyone for making it out to IoTDI virtually this year. In particular, I would like to say a big thank you before we depart to Ning and Husnu, who managed the IoTDI 2021 Zoom account, and just thank you all so much. I think you should all keep tuned for CPS-IoT Week correspondence about feedback on the conference. We would welcome your opinions and your thoughts. And with that, I will leave it to Haiying and Valerie for last words.
Valerie, you can go ahead.
Oh, I was not expecting that. So I don't have anything to add to Christopher. Yes, I would like to thank everybody from the organization for all the work, and especially Husnu and Ning. And the web chair, well, everybody was very helpful. And thank you for attending the conference, of course. So sorry I couldn't attend most of it, but thank you, everybody. Haiying, if you want to add something.
I would like to echo the messages from Chris and Valerie, and also thank you everyone for participating in this conference. Without you, the IoTDI 2021 would not be a bigger success. So we are so glad to see it's a greater success with the help of all of you. Thank you, and we look forward to meeting you in the near future. Please stay safe and healthy. Thank you, everyone.